At the smallest scales of reality, the ordinary rules no longer apply. An electron vanishes and reappears elsewhere, as if distance were a mere suggestion. A beam of light behaves like a spread out wave and, in the next instant, as a concentrated particle. There is a fundamental fuzziness in nature, a limit to what we can know about these tiny particles. Time and again, experiments reveal a universe that defies common sense, a universe where matter dances to the mysterious tune of quantum mechanics, utterly unlike the predictable clockwork of our everyday world. Today, we embark on a journey through this quantum realm, exploring its deepest enigmas, from particles in two places at once to the eerie bonds of entanglement, to understand how reality works at its core. Our journey begins with a deceptively simple experiment. Picture a barrier with two narrow slits and a blank screen behind it. Now, fire a beam of tiny particles, electrons for example, at the slits, one particle at a time. What appears on the screen? If electrons were simply little balls, you would expect two neat clusters aligned with the slits. Instead, something magical emerges, a series of bright and dark bands, an interference pattern reminiscent of waves overlapping. Each electron, though arriving as a single point on the screen, contributes to a pattern of alternating stripes, as if each particle passed through both slits at once and interfered with itself. This is wave particle duality in action, the revelation that matter and light can behave both like particles and like waves. Even more astonishing, if we watch the slits to see which path an electron takes, the interference pattern vanishes. The very act of observation forces the electron to choose a definite slit, and the wave behavior collapses into particle behavior. Measuring the particle erases the ghostly wave. This experiment, known as the double slit experiment, has become iconic for exposing the central puzzles of quantum mechanics. The physicist Richard Feynman famously remarked that it encapsulates the heart of quantum mechanics, containing the only mystery. Indeed, all of quantum theory can be gleaned from carefully thinking through its baffling outcome. How can an electron act as a spread out wave when unobserved, yet appear as a concrete particle when measured? How can it seem to travel two paths at once, yet never be caught in the act? In this quantum realm, reality shifts with perspective. The electron is neither wave nor particle until we interact with it, or perhaps it is both until we force it to decide. This is complementarity. The electron has complementary behaviors that cannot be seen simultaneously. As we grapple with this duality, we begin to sense the quantum enigma, a world where observation changes what exists, and where particles follow a logic alien to our macroscopic intuition. The disappearing interference pattern shows that observing quantum particles disturbs them profoundly. In fact, disturbance is not even the full story. There is an intrinsic uncertainty built into nature. This was codified in 1927 by Werner Heisenberg as the uncertainty principle. It declares that certain pairs of properties, like an electron's position and momentum, cannot both be known to arbitrary precision at the same time. In other words, the more precisely you know where a particle is, the less precisely you can know where it is going, and vice versa. This is not due to flaws in our instruments. It is a fundamental feature of the quantum world. Imagine trying to pinpoint an electron's location. To see it, you might shine light on it, but a photon of light hitting the electron jolts it, kicking it off course. The clearer you see its position, the more you have scrambled its momentum. But even if we could observe without disturbing, quantum theory says the electron simply does not have a perfectly well defined position and momentum simultaneously. The electron is described by a wave, spread out in space, and momentum. Try to confine that wave to get a sharp position, and it necessarily becomes a mix of many momenta, a wildly uncertain speed. This is the price of admission to the quantum world. The implications are profound. Under classical logic, one might imagine a tiny billiard ball electron with exact position and velocity. Quantum mechanics tells us that is impossible. The electron can only be described by probabilities, and yet this very fuzziness guards the stability of atoms and the universe. If electrons could spiral into the nucleus with definite trajectories, atoms would collapse. But uncertainty keeps electrons from being confined into the nucleus, preventing atomic implosion. Thus, the uncertainty principle is not merely a limit, it is a saving grace of the micro world, maintaining the structure of matter. Thus far, we have seen particles behaving like waves of probability. But what does it really mean to be a wave of probability? It means a particle can exist in multiple states at the same time, a phenomenon called quantum superposition. An electron does not choose a path at the double slits. It travels both routes at once until we observe it. In the quantum world, a particle can be here and there, or spin up and spin down simultaneously until interaction with the outside world forces a single outcome. The classic analogy is a coin spinning in the air. While spinning, it is not heads or tails, but a blend of both. Only when it lands do we get a definite result. Quantum superposition is that idea taken to the extreme, not as a blur from motion, but as a fundamental state of being. Perhaps the most famous illustration is Schrodinger's cat. Imagine a cat sealed in a box with a vial of poison triggered by a radioactive atom. Before we check, the atom exists in a superposition of decayed and not decayed states. This means the poison is both released and not released. So the cat, in theory, is both alive and dead at the same time. It is only when the box is opened and an observation made that the cat's fate chooses a definite state. Schrödinger intended this scenario as a critique to highlight how bizarre superposition is if taken to macroscopic levels. Indeed, in everyday life, we never see such superpositions. Yet, in the microscopic realm, superposition is utterly real. Particles do not have single histories, only a catalog of possibilities that coexist until checked. Superposition becomes even more mind boggling when it stretches across multiple particles. Enter quantum entanglement, a phenomenon so strange that Albert Einstein famously called it spooky action at a distance. Entanglement means that two or more particles can become linked in such a way that they share a common, unified quantum state, no matter how far apart they travel. If we prepare two photons together so that their properties are correlated, then separate them by an ocean or even light years, they remain entangled. Measure one photon and find it polarized vertical. The other is instantly found to be horizontal. It is as though information passes between them instantly, transcending space. This defies our usual sense of causality. How can an action here affect something over there immediately, with no signal in between? For decades, entanglement was debated as a paradox, but experiments have decisively shown nature indeed violates classical expectations. Entanglement is real, and no hidden mechanism can explain it. It tells us that at a fundamental level, separateness is an illusion. that the universe has threads connecting distant objects in a way the human mind struggles to grasp. From strange connections in space, we turn to a strange violation of barriers: quantum tunneling. Imagine standing before a solid wall. In our everyday world, you cannot walk through it. But in the quantum world, particles can do something astonishing. They can tunnel right through barriers that would be insurmountable in classical physics. An electron approaching an energy barrier does not always bounce back. Because the electron is also a wave, a part of that wave leaks through. There is a small but real chance the electron will simply appear on the other side, as if the wall were not there. Our sun shines because of tunneling. In its core, protons do not have enough energy to fuse classically, but quantum tunneling lets them slip through, powering the stars. Radioactive decay also often occurs by tunneling. With particles escaping nuclei they classically should not escape. This is no minor curiosity. It is a driving force of nature, and even the key to technologies like the scanning tunneling microscope and quantum devices. By now, we have seen how weird and wonderful quantum behavior is. But why do not we see these bizarre effects in our daily world? Why is Schrodinger's cat either alive or dead, never both? The answer lies in a process called quantum decoherence. Decoherence is what happens when a quantum system interacts with its surroundings. The moment a quantum particle collides with stray photons, air molecules, or anything external, its superposition becomes scrambled. The information that sustained its multiple states leaks into the environment. As a result, the system stops behaving in a quantum way and starts behaving classically. In effect, the environment is constantly measuring the system. The once spread out wave function appears to collapse, not from a single big measurement, but from the accumulation of countless tiny interactions. This is why we never see superpositions in everyday life. The quantum weirdness is drowned out by decoherence long before we could notice. We have explored the major quantum phenomena: wave particle duality, uncertainty, superposition, entanglement, tunneling, and decoherence. Yet one grand question looms: what is really going on in the quantum world? Physicists and philosophers have proposed many interpretations. The Copenhagen interpretation says the wave function collapses when observed, creating a single outcome from many possibilities. It emphasizes that the properties do not exist in definite form until measured. The many worlds interpretation, in contrast, says the wave function never collapses. Instead, every possible outcome occurs, but in different branching worlds. When you measure, you and the system split into parallel versions, each experiencing one outcome. Both interpretations fit the experiments. Both predict the same results, but they paint vastly different pictures of reality. One where observation creates outcomes, the other where reality endlessly branches into parallel universes. There is no consensus today. Quantum mechanics works flawlessly, but what it means remains unsettled. As our expedition through the quantum world comes to a close, we find ourselves filled with a sense of wonder. We have peered into a realm where particles dance on the edge of existence. Now waves, now particles, now something beyond. We have seen certainty yield to probability and solidity give way to shimmering possibilities. Quantum mechanics, for all its strangeness, is profoundly real. It underlies the very fabric of our universe, from the burning of stars to the microchips in our devices. It shows us that reality, at its most fundamental, is not solid and definite, but probabilistic and interconnected. That observation and interaction shape what becomes real. That separateness is an illusion, and barriers may be more porous than they appear. Richard Feynman once said, I think I can safely say that nobody really understands quantum mechanics, and yet, in that mystery lies the beauty. For the strange world of quantum mechanics reminds us that the universe is deeper, richer, and more mysterious than we could have imagined.